We are in our second notes of our unit on derivatives. Today we're going to take a look at the power rule for derivatives and the concept of differentiability. Alright, so last time I was with you, we developed a formula for the derivative, f prime of x. And you can use h's in the formula or delta x's in the formula, either one. They mean the same thing. So as long as you remember that h is delta x, you're in great shape. Okay? So let's say that we were asked to find f prime. You don't have to write all of this down, but let's say that we're asked to find f prime of this function. And we need to use the definition of derivative. Well, the setup for that, we know that f prime is this. So I'm going to replace every x with x plus h and then subtract that function. When I do that, I get this line. Okay? This is an example for a reason. I want to show you how tedious it can get. So now we have x plus h cubed minus 7 times x plus h squared plus 3 times x plus h minus 12 minus f of x all over h. We need to expand this more. So I need to cube this binomial. That is x plus h times x plus h times x plus h. And I need to square this binomial. And when I do that, I get a lot of terms. Okay, this is x plus h all cubed. That is x plus h cubed. I used Pascal's triangle to split that out so quickly, but the long way would be much longer to do. Here is the negative 7 times, oops, one more here. There's negative 7 times x plus h squared, and there's 3x plus 3h minus 12, and then I ran out of space here, so I subtracted f of x right there. Okay, when I combine all of my, things should cancel, right? This x cubed cancels with this x cubed. Anything without an h should cancel. When you see an h, it shouldn't cancel with anything. Here's a negative 7x squared, positive 7x squared. H, positive 3x, negative 3x. H, and then here's a negative 12 and a positive 12. They should cancel. So I'm left with this. Okay, everything on top has an h in it. So I can factor out an h, and then reduce those h's. Okay, reduce these h's. I'm left with this. Now oops, I made a little right-o here. I changed my h's to x's all of a sudden. H is going to 0. And now we put 0 in for any remaining h's. So we'll have a 3x squared, that'll be a 0, that'll be a 0, negative 14x, that'll be a 0, and then the plus 3. So we found that if f of x is x cubed minus 7x squared plus 3x minus 12, f prime of x will be 3x squared minus 14x plus 3. That's what we found. Can you imagine if we had a function that was 7x to the 9th plus other things, 1 over x plus 1, bunches of other things. How tedious that would get. How tedious the definition of derivative work becomes. It becomes very tedious. Is it impossible? No, we could do it. But it is very tedious. It's very easy to make mistakes. Okay? So, mathematicians noticed a pattern. And you might notice a pattern. If we did a lot of examples, you would probably notice a pattern. Okay? if I ignore this for now because that makes it more complicated, but if I change that to an 8x to the 6th, I would tell you that if we worked all this out, if we did all of the limit process, we would get 63x to the 8th plus 48x to the 5th for our derivative there. So what is the pattern? What is happening? Okay. Well, the pattern is if your function has an x to a power, if you have an x to a power, then you multiply the power times any coefficient that's there. So 9 times 7 is 63. Keep your x, reduce the power by 1. This one would be 48, x to the 5th. Okay, so what we did here, 3 times the coefficient, well, the coefficient is a 1, so 3 times 1 is 3. Reduce your power by 1. 2 times negative 7 is negative 14. Reduce your power by 1. The derivative of 3x is just 3. You can think of it as this power is 1. 1 times 3 is 3. When you reduce your power by 1, you get x to the 0, which is just 1. Regardless, when you take the derivative of 3x, you're always going to get 3. And what happened to this negative 12? The derivative of any constant is 0. So this is the power rule for derivatives. The power rule for derivatives. If f of x is x to the n, where n is any real number. It can be positive, negative, it can be a fraction, it can be pi, it can be any real number. It can be a square root, anything, a negative square root. It can be a negative fraction, a positive fraction, any real number. Very important that you realize that it has to be a number. It cannot be a variable like another x. All right. If f of x is x to the n, where n is any real number, then f prime of x is, you're going to multiply the exponent times any coefficient, and then keep your x and reduce the power by 1. So n minus 1. Power rule for derivatives. This is a lifesaver because we don't have to go through the limit process to find a derivative. If our function is in the form x to a power. That's crucial. Our function has got to be in the form x to a power. Okay? Let's look at some more examples. Example 1. Let's say that f of x is x squared plus 1, and we want to find the derivative. Okay? Take your power, multiply by any lead coefficient, keep your x, reduce your power by 1. The derivative of any constant is 0. Clean it up, 2x. That's it. The derivative of x squared plus 1 is 2x. Next example, g of x is 5x to the 9th. What is g prime of x? G prime of x. Take your exponent, multiply by any coefficient, keep your x, reduce your power by 1. 45x to the 8th. Okay. H of x. negative 2x to the 7th plus 5x to the 5th minus 3x squared plus 17x minus 20. That would be a nightmare to use the limit process to find this derivative. But with the power rule for derivatives, it makes short work of it. 7 times your coefficient. Reduce your power by 1. 5 times your coefficient. Reduce your power by 1. 3 times your coefficient. Reduce your power by 1. I'm not going to write a 1 there for that power. The derivative of 17x is just 17. The derivative of negative 20 is 0. Okay? Another one. Let's call this one j of x. J of x is equal to the cube root of x minus 5 over x cubed minus 7 over the 5th root of x squared. Find j prime of x. Okay? All right. We have to get our function to be in this form for every term. It has to be on top, the x has to be on top, and it has to be x to an exponent, not square root or anything like that. We have to change this to where it has x to a power for every term. So before we jump in and take the derivative, we need to change the look of j. So the cube root of x is x to what power? We need to change that cube root to a power. Well, the cube root of x is x to the 1/3. We learned that last semester. When you move an x, we need to move this x to the top. When you move the x to the top, it'll be a negative exponent. So minus 5x to the negative 3. Okay? This will be a negative 7x to a negative power because we're bringing it to the top. What power will that be? The root is always in the denominator of your exponent. So to negative 2/5 will be the power on the x. Okay? Now every term is in the form x to a power. That is a number. So now I can come in and find the derivative. Power times any coefficient. Reduce your power by 1. What is 1/3 minus 1? 1/3 minus 1 is a negative 2/3. Power times coefficient. Positive 15, x to the, reduce your power by 1. Negative 3 minus 1 is negative 4. Power times your coefficient. Okay, well, it'll be a positive because a negative times a negative is a positive. 7 times 2/5 is 14/5. 7 times 2 divided by 5. 14/5. X to the negative 2/5 minus 1. Negative 2/5 minus 1 is negative 2/5 minus 5/5. That is negative 7/5. There's your derivative. Right there. Okay. Let's do another one. Let's just call this one y. Y is equal to, okay, let me make this up, 2x to the 4th minus 3x cubed plus x squared minus x minus, let's call this 7x plus 5, all divided by x squared. Okay, all divided by x squared. Okay, we have to get this all into just x to the n power. It has to be x to the n power. This is definitely not x to the n power. This is a quotient, right? So we have to do this. We have to get it into it's all just x to a power. So I need to divide. I need to take, I call this a quickie divide. When you have one thing in the denominator, I'm going to divide everything on top by the denominator. So everything on top by the denominator. Okay? When we do that, so I'm rewriting y. 2x to the fourth divided by x squared is 2x squared. Subtract your powers. Okay? Minus 3x to the, what happens to the x's? You're left with 1 on top. So just 3x to the first. Plus, okay, what happens to the x's here? They cancel out. What do they cancel to? They cancel to a 1. They reduce to 1. Okay? Negative 7x over x squared. Okay? It would be a minus 7x to what power? I'd be left with an x on the bottom. I need to bring it to the top and give it a negative 1 exponent. Here we have a plus 5x to what power? We have to bring it to the top, give it a negative exponent. So you have to rewrite y into all just x to a power, x to a power, x to a power. And then you can come in and find the derivative. So we're taking the derivative of both sides with respect to x and power rule time. So 2 times your exponent, keep your x, reduce your power by 1. It'll just be a 1 there. The derivative of negative 3x is negative 3. The derivative of any constant is 0. Okay? Power times coefficient, we'll make this a plus 7 x to the, reduce your power by 1. Power times coefficient, reduce your power by 1. There's the derivative. As a multiple choice answer, you might see this as 4x minus 3 plus 7 over x squared minus 10 over x cubed. They might move those exponents, those x's back down to the denominator at the end. Or they might just leave it like that. All right. So that was one example of everything I think that you will see now in power rule for derivatives. And I keep saying power rule for derivatives because we do have a power rule for integrals that we will get to when we do integrals. Okay, now I'd like to talk about something called differentiability. It's a big word, and it just means the derivative exists. Okay, differentiability, we say that a function is differentiable if its derivative exists. Okay? So I might say it this way. A function is differentiable at a point if the derivative of the function exists at that point. So you might be thinking, what do you mean? Doesn't the derivative always exist? And the derivative does not always exist. Remember that derivative means the slope of the tangent line. So for one thing, what would make the slope of the tangent line not exist? Think back to Algebra 1. You had some, when you were dealing with slope, when you were when you were considering slopes, there were some slopes that did not exist. They were undefined. What would make a slope undefined? Well, a slope would be undefined if the line was vertical. Okay? So there are actually three things that would make a function not differentiable. So f of x is not differentiable at x equals a if, okay, one of them is the tangent line at x equals a is vertical. So f has a vertical tangent line at x equals a. So if f has a vertical tangent line at x equals a, f is not differentiable at x equals a. Okay? Another thing that would make a function not differentiable at x equals a is if f is not continuous at f equals a. That would make also f not differentiable because it's not even continuous. Maybe it has a hole at x equals a. Maybe it has a vertical asymptote at x equals a. Maybe it has a jump discontinuity at x equals a. So might graph that for you. If f has a jump or a hole or a vertical asymptote, then f is not continuous at x equals a. F is not differentiable at x equals a. A vertical tangent line, that kind of a graph, would look maybe something like that, where you have a vertical tangent line right here. Okay? There's a third reason. There's a third reason that would make f not differentiable. And that is if the slope from the left is not equal to the slope from the right. A couple of ways we could think of. I like to think of maybe an absolute value function. An absolute value function. We've had some absolute value functions that do this, where they flip in the middle. This right here is called a cusp. The slope from the left is not equal to the slope from the right. So f has a sharp, I'm going to call it a sharp turn. F has a sharp turn at x equals a. That's also called a cusp at x equals a. So that would make f prime not exist. So f prime does not exist if any of these happen. Okay, we need to know those three reasons that make a function not differentiable. Okay, so example 1. Let's say that f of x is x squared minus 9 over x plus 3. Okay, get to where you can see this. Okay, at what value of x, the question would say, at what value, or maybe state any values of x at which f is not differentiable. Okay, so in this one, what value of x would make f not differentiable? Well, I see that there is a denominator, and I know that f would not be continuous when the denominator is 0. So this one would be I would say f is not differentiable, and we abbreviate differentiable with DIFF because it's a rather lengthy word to keep writing over and over and over again. F is not differentiable at x is equal to -3. Because f is not continuous at x equals -3. If they wanted a reason, I would say, since f is not continuous at x equals -3. Okay? Here's another one. F of x is the absolute value of x squared minus 5x plus 6. When you see an absolute value function, you know there's going to be these cusps. And the cusps happen when the graph flips from negative to positive, positive, negative. So I need to find out what makes the interior of my absolute value 0. So I'm going to factor it. X and x, 2 and 3, negative and negative. So if I were graphing this, when x is 2 and 3, we would have zeros. Otherwise, it's a parabola. So this parabola would be doing something like that. Okay? Something like that. So f is not differentiable at x is equal to 2 and x is equal to 3, since f has a cusp at x equals 2 and x is equal to 3. The slope from the left is not equal to the slope from the right. They're not the same. So cusp and not differentiable. Next one. What about f of x is equal to the cube root of x? Okay, well, this is continuous everywhere. There's no denominator. It's continuous everywhere. And this is a smooth graph that has no cusps. So is it ever not differentiable? Okay, these are a little bit harder to find, or harder to notice. It's harder to notice when you have a vertical tangent line somewhere. Here's how to do it. Take the derivative. Go ahead and take the derivative of this. The cube root of x is x to the 1/3. So the derivative is 1/3 x to the, reduce your power by 1, negative 2/3. That is 1 over 3 x to the 2/3. The derivative, it has a 0 in the bottom when x is 0. Okay? That means the slope is undefined when x is 0. That's a vertical tangent line. So f is not differentiable at x equals 0, since f has a vertical tangent line when x is 0. Okay? Alrighty. So that is the power rule for derivatives and the concept of differentiability.